or what?
Yes. طيب بسم الله الرحمن الرحيم. I'd like to welcome everyone to this important event by Dr. Ayman Al-Malh and Dr. Ashraf. The title is Introduction to Machine and Deep Learning. We'll have about 6 hours divided into 2 parts, and every part is divided into the morning part is divided into two parts also. So we'll have a break in the middle, and also in the afternoon parts also we'll have a break in the middle, inshallah. Before we start, let me just introduce our speakers. I'm sure most of us they know them. The first speaker is Dr. Ayman Al-Malh. He is a professor and the chairman of the Computer Engineering Department. He received his BS degree in computer engineering from the KFUPM as the first honor in 1989. His master in electrical engineering from the University of Victoria, Canada in 1991, and his PhD degree from McGill University in 1995. His research interests include artificial intelligence, deep learning, and hardware acceleration of deep learning algorithms. He has developed and taught courses in artificial intelligence and deep learning. He received several awards, including Best Paper Award for the most outstanding contribution to the field of test at 1995 European Design and Test Conference. He received the Excellence in Teaching Award from KFUPM twice in 2001, 2002, and 2006 and 2007. Actually, more than that, 4 times, sorry. 4 times. And his Excellence in Advising Award twice in 2013 and 2014, and in 2017 and 2018. His Excellence in Research Award from KFUPM in 2010 and 2011 and 2015, 2016, and the first Instructional Technology Award from KFUPM in 2009, 2010. Our second speaker is Dr. Ashraf Mahmoud. He is a professor in Computer Engineering Department. He received his BS degree in Electrical and Computer Engineering from Kuwait University in 1990, and the Master in Computer Systems and Artificial Intelligence from McMaster University, Canada in 1992, and his PhD in Systems and Computer Engineering from Carleton University, Canada in 1997. During 1997 to 2002, he was with Nortel Networks Research and Development, where he focused on the development and evaluation of radio resource management algorithms for broadband and 3G networks. So without further ado, I would just hand it over to our speaker. Dr. Ayman, I think we'll start. Yes.
Bismillah ar-Rahman ar-Rahim. I would like to welcome you to this workshop. Just give a brief overview about this workshop. The objective of this workshop is really to give faculty an introduction about artificial intelligence, in particular what we cover in the undergraduate course, CO 292, that is offered for all undergraduate students at KFUPM. So our objective is really to give you a brief overview of what we cover, in particular in the machine and deep learning parts, because these are the most practical parts that might be used by in different majors, so that faculty can get an idea about what students take, so that they can build on this knowledge that the students cover in this course and utilize this knowledge in their courses, so they can ask students to do some applications based on what they have learned in this course. The workshop is introductory course. It's compressed version because we have to do it in one day. So it's going to be having 2 sessions. The morning session will be focused on machine learning, and that will be given by Dr. Ashraf in 2 parts. And then the deep learning part will be given by me in the afternoon session. also that will be divided in 2 parts. So I think that maybe the best way is to have an interactive like session. So as we explain, we go over the material. If you have any question, clarification, you may ask right away and we clarify it. We have shared the material in the Blackboard account and the notebooks that we're going to use so that you can have access and you may try as we demonstrate some of them. We're going to use the Google Colab basically as the platform for illustrating the notebooks. You don't need to install anything. So just like we will show you as we illustrate the notebooks. So I'll hand the floor to Dr. Ashraf to start the first session on machine learning.
Bismillah, alhamdulillah, wassalatu wassalam ala rasulillah. Thank you very much, Dr. Ayman and Dr. Mujib for this introduction. Without further ado, let me start the first part on machine learning. I'll share the screen. Okay, so for the first part, the first part is about supervised learning, where we spend time on KNN and perceptron and support vector machines. So the first presentation is on the first 2 items, KNN and perceptron. Let me just okay. So the outline for my session is one part about supervised learning, which includes KNN, perceptron, and SVMs. We will also touch on boundary decision evaluation and how is that evaluated. Then we will move to unsupervised learning, where we focus on k-means, and then semi-supervised learning, where we take some simple example of Q-learning. Okay. Initially, we show the students what are the applications, general applications of machine learning, which range from classification, clustering, regression, and association rules, and finally reinforcement learning. For supervised learning, we start with this very simple and intriguing example where we show them digits and we ask them to, how would we identify a given drawing of a specific digit. Okay, so we have a data set where we have mapped the images to outputs, like the specific digit that it represents. And then if we show them an input that is not mapped to anything, how would we classify it? Okay, so this is a classification problem, which is one of the most important problems to solve. And we highlight that computers must classify these things into categories based on the given examples. So we give the examples, we give the images that are already labeled, and then we want the computer or the AI machine or the program to classify an input that is not labeled. So this is supervised learning because we are giving the labels, and the function that is producing the classification or the label for the unclassified input is what we are after, which is the classifier. We also give this example where we are trying to predict the weather. We are collecting information about temperature, humidity, and maybe other factors. And we would like to classify that weather set, whether it's a rain or not rain event. Okay. So the question is, can we come up with a function to model or predict the weather given the inputs, which are temperature, humidity, and other things? And basically, we would like to build a classifier for that. The original data may include more than one feature, but for simplicity here, we will focus on 2 features, pressure and humidity. So this is a drone sample where we have rain or no rain based on humidity and pressure. And we are asking the students, to think about this data set and how we can see that some of the points are they are not perfectly separated. And given that we have two features, that this is a 2D plot, for example, what would happen if we have more features, if we have more classes? And then we ask them to classify like an unknown point like this point here, which has a question mark. Okay, so the natural response would be that this point would be a rain event. So the humidity and pressure values that correspond to this point should be classified as a humidity, as rain. And the approach that the students would come up with is that this point lies among the points that are rain in general. So in this way, we introduce the concept of neighbors and the distance between these points. Okay, so again, this point is classified as blue, yani there is a rain, and it is the nearest neighbor that it has is a blue point, yani there is a rain, and that's why it should be classified as such. And then we ask about another point, which is now in the other camp, which is no rain. And the classification is simple also because the nearest neighbor is also red, and therefore it should be classified as no rain. And then we take this idea further by including now, we have a point which has, the closest neighbor is red, but it looks like it should be classified as blue. Why? Because the majority of the neighbors around it are blue. So this is where we build up to the concept of KNN algorithm, the nearest neighbor, and it's based on K points. Not simply one, it could be any number that we pick. Okay, so for example, for this point, which has a question mark, okay, if we consider only a single neighbor, then it should be classified as no rain. But if we consider, for example, the closest three neighbors, then it should be classified as rain. Okay, it should be classified as rain. Now, once that concept has been emphasized, now we look at how do we measure that closeness or similarity between the points. In this course, we introduce only these three similarity measures. The first one is the Euclidean distance. It's a very simple, the straightforward Euclidean distance between the points given the coordinates. Okay, this is probably given by this very famous equation, which is the square root of the sum of the difference in the squares of the coordinates. Okay, and we are giving here an example of 2 points. And based on these 2 points, we are calculating the distance. Okay. Another similarity measure that's also explored in this course is the Manhattan distance. Okay, the Manhattan distance is simply the sum of the absolute value of the difference in the coordinates. So this does not involve a squaring, and it does not involve a square root. Okay. And for the same example of points, we are computing the Manhattan distance as shown in the example in the slides. Okay. So this is the this is the difference between the Euclidean distance and the Manhattan distance. The distance, the direct distance between start and destination is given by the Euclidean distance. But if you go and add A to B, then that gives you the Manhattan distance. Okay. This is a numerical example. We start these type of problems by giving 4 points. 2 are labeled blue and 2 are labeled red. And then we ask about this point with a question mark, which is at coordinates 3, 7. And then we ask what should it be labeled. And we are asking them to use a 3NN algorithm using the Euclidean distance first. Okay. And for that, they have to list the points. Okay, the 4 points, these 4 points that are given in a table format like this. They compute the distance between each of these 4 points and the unknown point. And these distances are as given in the third column. And then we rank them. Okay, we rank them. We look at the least 3 distances, and we check which ones, how many are good and how many are bad, how many are blue or how many are red. And in this question, we find that two of them are good and 1 of them is bad. And therefore, this point, which is unknown, the question mark point, should be classified as good. The same question could be repeated with the Manhattan distance as well, and the students will go through the exercise. Now, another point of similarity that we, another similarity measure that we explore in this course is the dot product. And this is particularly useful for images. Okay, so for pixels, we assign the intensity. We assign a vector of intensities that represent the image itself. And usually this vector of intensity values is normalized to values between 0 and 1. Okay, and then we motivate. The idea is that when we look at vectors, if we want to look for similarity measures between the vectors, then the dot product is a natural candidate for looking at this. And in this slide, we represent the idea of dot product. So assuming we have 2 vectors A and B, and each of these 2 vectors could represent an image, so that we have an image A and an image B. And then we define the similarity between these 2 images as the dot product. And the dot product is, as we know, it's a very simple sum of multiplying the corresponding components, and that's all. Okay, it's also given by the magnitude of A times the magnitude of B times the cosine, and from there we can ask questions about like what happens if these 2 vectors are very dissimilar. What should be the dot product look like? And now we point out, since we are only dealing with intensities that are between 0 and 1. So these vectors are not general, so they cannot have like negative components. And if we normalize the component, the magnitude of each of these vectors to 1, then this dot product is always between 0 and 1. And it is 0 when these two vectors or these two images are there is a maximum dissimilarity between the 2 of them, and it's equal to 1 when there is a maximum similarity. And I think even we highlight what would be the case if we have negative components, and therefore the similarity would be -1. -1 would be 2 similar vectors, but they are in completely opposite directions and things like that. So we have this part of this KNN on dot products and comparing images. Now, finally, this part is concluded with like a summary of the summary of the KNN protocol. It's very simple to use. It does not require any training for a priori model. The cons is that it's very slow in classifying a new point, and it would require measuring the distances. And if you're using Euclidean distances, sometimes this is computationally expensive, and maybe you have to sort even the data points. If you have a large number of them, it will be inefficient. Okay, we have a tool that shows that, and we have some of the Python notebooks that I will go through. Let me just get out of this. And how do I access my my program? I don't want this. So
Especially if you have to share the whole screen. Now it's okay.
what should I do?
No, you are sharing the whole screen rather than just the application. So it's we can see the.
Should I change the sharing mode?
Just try if you face it. If if we are not able to see, I'll let you know.
Yeah, for example, this is the KNN part. This is the KNN Python. This Python notebook is about iris flower species data set, and we are trying to classify the data. In this specific file have 4 types of the iris flower, and it's like an Excel sheet. It's being read from a website. It's originally a comma separated values Excel sheet, but we can also read it from this website. So initially we import these classes, and then I'm going to go through this very quickly. Now in this part here, where this is where it's reading the data from. So it's reading it from some university archive. Okay, and it is also showing it's showing the head of the data set that it has read. So we're just showing the first 5 rows of that. And the classes, you can see the features that they are looking at is the CPAL length, CPAL width, and BITL length and BITL width. So we have 4 features, and we have 4 classes. They are all different species of the iris flower. Okay. So initially we pre-process the data as highlighted in this. Okay. Let me just. So we take the first 4 columns as our text, which is the features. Let me just run this, and we take the last one as the label, which is the class. Okay, and then we split the data between training and testing. We will be talking about that in the probably second session. So we set it here where 80% is used for training and 20% is used for testing. And another thing we also do in this notebook, which was not highlighted in the class, which is feature scaling. Now, in the class, we present the main ideas, but when we go and explain these notebooks, we go into some of these details, which are not major parts in the slides themselves. So what we do here is feature scaling, and we show that. And there was a programming assignment given to the students to show that if you do feature scaling, then the performance of the algorithm improves. Okay, because that makes computing the distances fair between different when you have features that have probably the same zero mean, for example, and unit variance. So here we do feature scaling, and we use this normalized. Now we have X-train normalized and X-test normalized. And for this particular notebook, we're plotting them. We're plotting the features before being normalized, and this is shown here in this graph, which is before scaling. And then we're plotting them after scaling. And we can see that now the features are more well behaved. They have roughly the same range, and they have unit variance. So when you compute distances based on these features, it's more fair relative to the initial case. Okay. Now we use these normalized features. We generate them again and remove the underscore normalize so that we use X underscore train and X test. And we call this K neighbors classifier from the sklearn class. And we give it that we want to classify using KNN5. And we pass the X train and we pass the Y train. Okay. Do it. And this generates the model, and now we want to test it. So we pass the X test to it, and it generates a Y prediction. Now, this is the predicted based on the model that was created with KNN equal to 5. Okay, and this Y prediction here, which is this one here, this one needs to be compared against the labels that are originally with the data. And that creates the classification metrics, which we did not go through yet. Okay, like for example, you can evaluate accuracy, you can evaluate recall, you can recall many of these. I don't know what's happening here. It's not. So we can generate confusion metrics. You can all these metrics the students can generate. Okay, for example, in this case, we are generating. Let me just scroll down. In this case, we are generating a confusion matrix for 3 classes. And this is a table that shows the precision and the recall, the F1 score, and the support for the model that we have computed. Okay, we can also show in this notebook how does the error change as the K varies in the KNN. So there is a code which allows the, which is given here. We can plot the error or the mean error versus the K and try to find out what is the optimal K for this data set and this for algorithm. I think that's mostly, yeah, this is here what we are doing is we are trying to draw the decision boundary for this algorithm. And this is based on what we do is we create a mesh grid for all the points. Now we have already created a model that would classify the point, whether it's of type yellow or type purple in this case. We have 2 types. So we are only focusing on 2 types, whether it's of type yellow or type purple. And the model has been created. And then the mesh grid contains all the points in this 2D plane. And we pass it to that classifier, and it will tell us how it would classify that point. And based on that, I would color the region. And this gives us these graphs. And these graphs describe the decision boundary between what is classified as yellow and what is classified as purple. Okay. So that's basically this notebook. And I think in this semester, the students were given an exercise to do some of these ideas around these ideas, but with different data set and different types of classes. So the students learn about the learn about the theory in the slides in the class, and then we explain the notebooks. We go through the notebooks and the code in the class as well, but then sometimes they have also programming assignments where they have to take this and apply it into different data sets and probably some tweaks in the code as well. Now, this concludes the first part, which is the KNN. Now we go into the second part. Okay. The second part is about we motivate if there are other classifications approach that could be done other than the KNN. And we are asking them to, if we could draw a decision boundary between these 2 points. And based on this decision boundary, we can classify points, unknown points, like these points that are shown in question marks. Okay. So the yellow line here represents one possible decision boundary that could be drawn. And for this specific example, this decision boundary is separating the rain days from the non-rain days. Okay, so there is a clear separation. These points are linearly separable. So this is a very simple example. And then we are asking about what is the label of these unknown or question mark points. Okay. So classification by creating a decision boundary now is motivated. So we are how would we draw this line? So there may be different algorithms that can be used to find the best decision boundary. Okay. Now we also highlight that if we are talking about 2D, then the separation, the boundary is a 1D object, which is a line. Okay. In 3D, it would be a plane, which is 2D. Or in ND, we have N features, then it would be a hyperplane. Okay. Now, for this to work, or at least for this simple idea to work, the data has to be completely separable. Completely separable. And then we will look at what would happen if the data is not separable when we talk about support vector machines. So the general idea here is how do we come up with this best line decision boundary? Okay. This is an example of the same data. We have some overlap between the rain and no rain. So you can see 2 points that are rain. They are above the line or above the multiple lines that could be drawn. So these 2 points would be classified wrongly. And we have also another red points that are also below the line. So these are also could be classified wrongly based on these 2 lines. Now the lines that could be drawn between these 2 camps or 2 classes, they would have this simple linear equation AX1 plus BX2 is equal to C, where X1 and X2 are the features themselves, so the humidity and the pressure. So we would like to find this line, okay? And develop a function h, we call it h. You give it the 2 coordinates, x1 and x2, and based on that line, it will tell me whether the point should be classified as rain or no rain. Now, this equation for the line can be written as shown here as W naught plus W1x1 plus W2x2 equal to 0. This is an equation of the line in the general case. Now, the x1 and x2 are the features themselves, but the W0, W1, W2 are the weights, and these ones have to be computed. For every different combination of weights, we have a different line. So we would like to find what's the best line. And using this line and its coefficients, its W's coefficients, we would like to build this function, x1 and comma x2, that gives me this classification. And later on, we will be evaluating this classification function. And right now, we say rain or no rain if W0 plus W1x1 plus W2x2 is greater or equal than 0. Otherwise, it should give me no rain. Now, we try to formalize this. Now, the W coefficients are put as a vector. So we're looking for a W vector, which has 3 components, W0, W1, W2. And the X itself, which is the input, is put as a vector where the first component is only 1. So we have 1, comma x1, comma x2. This allows us to write the equation of the line as a dot product between W and X. So the X function now, the H function now can be written as it's equal to 1 if the dot product between W and X is equal or greater than 0, and it's equal to 0 otherwise, okay? And that should allow us to classify the points based on x1 and x2. It should return to us either it's 1, meaning it's rain, or it's 0, meaning it's no rain. And this is the final form of the classifier, the h of x. So it's we pass it the features x for given coefficients w. It would compute and return to us whether this input is rain or no rain. So this is written in a more compact vector form. So the perceptron now till now we were talking about this line which separates between the two classes, which is specified by these W's, but we did not say how to come up with these W's and how to compute them. Okay, so initially we start with some W's, some line, it has some W's, and we would like to update it. We would like to search for the best line that separates between this. So we start considering the data points, and we update the W's by considering each data point. And considering the data point may lead to an update in the W vector, or may leave it as is. It depends on where the data point is located with respect to that line. So for this example here, so we given a data point xy, we use this update perceptron formula for updating the coefficient w sub I, which says that the new coefficient is equal to the old coefficient plus alpha, which is a learning factor, which is something that controls how fast you update your coefficients, times y minus the prediction. Y is the actual class, h is the predicted class, and we multiply that by x. Now, if the actual class y is the same as the prediction x, the prediction h, it means the new w is the same as the old w, so there will be no updates. But if these are different, then the new w will be different than the old w. Okay, this is explained in this slide, where we compare the actual to the estimate. Estimate is what we get from the h function. The actual is the y, which is the original class for that. Remember, we're using we're still doing with supervised, so we have the labels for the data points. So we are asking the students, given a data points that have labels, can you find the best W's for that describe the linear boundary that separates between these points? So they have to go through this procedure. This is the algorithm, that perceptron algorithm. So if we have more points, like in this case, we have T points, capital T points, and there are n components for the vector W and X. So we go through the points from 0 all the way to capital T, and this would be one round. But then you may have to go through another round and a third round, as long as you will find that the classification error will change from one line to the next. And usually after you go through several rounds, you are looking for the minimum classification error. So you will come up with a line that has minimum classification. Now, if the data is perfectly separable, then you will reach a line that has zero classification error. But if the data is not, then you will be looking at the minimum classification error. And we also motivate the learning update procedure that we just talked about when updating the coefficients using geometry and graphs. For example, in this case, we have blue lines and we have red lines. Sorry, we have blue points that are labeled 1, and we have red points that are labeled 0, and we have this initial line, and the W vector is as shown. Okay, I did not mention, but the W vector is always perpendicular to this decision boundary. Okay, we can show mathematically that it's always perpendicular to the decision boundary, and it's always pointing to the, when it's in the right position, it's always pointing to the positively labeled points. Okay, so in this case, it should be pointing towards the blue points in this case. So let's assume we have this kind of situation, and now we are updating the W based on the points that we are having. For example, in this case, he is considering this point. This is a misclassified point. Okay, this is a misclassified point. This point is blue, so it should be with above the line, but it's below the line. Okay, so its original class is 1, but the prediction is 0 because it's below the line. So the h function evaluated for this point is going to be 0. So when we apply the learning rule, we find that we have to add this vector, which is the data point, the vector, to the W vector. And this is what we are showing here. So this is the original W. We add this vector here, which is the point. This is the same as this vector here. We add it and we update W, and this is our new W, the one which is written in yellow, okay, highlighted in yellow. This is for considering this point. This is when we consider this point. Now, for another situation, when you update the W, remember W is always perpendicular to the decision boundary. So now the line has changed. Now the line is almost vertical. Okay, the line is almost vertical. Okay, but this line still misclassifies this red point. Okay, this line still misclassified this red point. I don't know if I can write on it. Well, this point here, this point is still misclassified. Okay, this one here, and therefore we follow the same procedure. The actual is 0, but it is being predicted as a 1, and therefore when we apply the learning rule, we will find that we need to subtract this vector from W. And when we subtract it, as shown in this graph, the W changes from this direction to this direction now. Okay, it's not allowing me to this direction. And since the W has changed, it means the new boundary is the new red line, which is shown here. And this line here is classifying all points perfectly. Okay, this line is classifying all these points perfectly. This is a numerical example. We have some data points. And we have an initial W. This is the initial W. Okay. And we ask the students to go through the numerical example and to see whether the W vector is updated for each one or not, and show what is the update value for the vector. The learning rate here is alpha equal to 0.01. Okay. So for example, we start with this initial W. And now considering the first point, these are the two features, but we have to add 1. As I said, x0 is always equal to 1. When we do the dot product between W0 and W1 and evaluate and check what would that be, it would be equal to 2, which is greater than 0, which means we are this point would be predicted as 1. And also the actual is equal to 1. So there is a match between the prediction and the actual. And therefore, in this case, we don't update the W's. The W's remain as is. So we have the same W's here. Okay, the same W's here. Now for the second point, now this is the second point. These are the two features, and we add 1 to them here as x0. We do the dot product between the W and the input x and evaluate that, and that comes up to be 0.4. And 0.4 is greater than 0. So this point should be, it's predicted as 1, but the actual label is 0, which means when we apply the learning rule, we are going to do W plus 0.1 times 0 minus 1, because the actual is 0 and the predicted is 1, which means we are going to subtract part of x from W to update W. Okay. And after going through this calculation, this becomes the updated W. Okay, so what we did is we subtracted part of 0.1 of x from the W, and this is the new update for W. And the students have to go through, the third point, we'll find we don't have to do any update. And this one, we don't have to do any update. The third one and the fourth one and the fifth one. For this example, I think there was only one update. Okay, now in the assignment, we give them more points, more variety. We have questions based on graphs. We have questions based on listed points. And students are deal with different types of decision boundaries that are, and for example, here we were looking at decision boundaries that have slopes. We can deal with decision boundaries that are vertical, so no slopes, or perfectly horizontal, the slope is equal to 0, and things like that. They go in the assignments, they go through all these variations. Now for to motivate before we finish the perceptron algorithm, we leave them with this idea, which is going to be more relevant when Dr. Ayman talks about neural networks and the sigmoid activation function. On the right, we show the same data set, and we ask about the classification of the points 1 and 2. For both of these points are below the line, so they would be classified as blue. Okay, so but the question is, how sure are we that these points 1 and 2 are blue? Okay, now it's clear, for example, that point 1 is very close to the line. So although it is classified as blue, but we are less sure that it is blue compared to the point which is 2, because point 2 is very far from the line, and it's really deep down in the region where points are blue. And this is all due to the fact that the threshold function that we are using is a hard threshold function, so which is shown here. Okay, so we have a threshold function. We are computing this. We're computing this dot product, and we are comparing it to a threshold of 0. If it is below 0, then we are labeling it as a 0 class, and if it is greater or equal to the threshold 0, we are labeling it as a 1 class. So we have a very hard threshold function. And that hard threshold function doesn't give us an idea how close the point or how far the point is. But if we use something like a soft threshold function, like this one here, okay, then it would return a number between 0 and 1. And that number could be used as a probability number or a probability figure. It reflects maybe how sure you are. For example, for the point 1, it may return something like a low number. So it is classified as blue, but maybe with low probability. But for the point, for example, 2, it may be classified as it is classified as blue, but with high probability. Okay, and this is if we use these soft thresholds, and this would be like a motivation for the activation functions later on in topic 5, where they go for neural networks and deep learning using neural networks. Now for the perceptron also, we have a notebook which is on perceptron. This notebook is here. Okay. So this notebook also uses the same data set which is classifying the iris flower species based on the 4 features. Okay, so we call these classes. We upload the data set. Okay, and we show the head of this data set. And for this, we plot the scatter plot to show them that we are looking at 3 species of the iris flower. So we do a scatter plot using the colors red, orange, and blue. And now we use the sklearn to here he's just loading the iris, trying to. Okay, so he wants to classify the points based on 2 features only out of the 4. And he's classifying all the data points into iris setosa or not iris setosa. So rather than dealing with 3 features, he's dealing, 3 classes, we're dealing with 2 classes. Iris setosa is 1 class, and everything else is the other class, which is not iris setosa. And we are trying to use these 2 features only, the betal width and the betal length. So if we do this plot, we can see that the data is clearly linearly separable, which lends itself to perceptron algorithm to be used for separation. So here we call this perceptron method. We want to do 1,000 iterations, and we use the learning factor of 0.5. Okay, and then we do the fit. So we pass it the training and we pass it the labels, and it does the fit. Now the coefficients have been computed for that line based on the 1,000 iterations. Again, here we would like to draw the boundary. So we do a mesh grid. Okay, so this is a mesh grid for all the points in the 2D region. And then we pass every point to the predictor, and we get the prediction. And then we color the region based on the prediction that we got. And we plot that. So we got this. So now we have the line is the separation between these 2 colored regions. And it is perfectly separating between the iris setosa points and the not iris setosa points. So there is a clear linear boundary separation between these 2 points. Well, we can also evaluate how well does this do in terms of performance. So we divide the data into training and testing. Then we do the training, and then we do the testing, and we can print the confusion matrix and the accuracy measures for this. Okay, and if we go down below here, this is the confusion matrix, and these are the precision, the recall, and the F1 score for the model that was developed. Okay. This concludes the first part, which is on KNN and perceptron. Okay. Are there any questions before I move to the second part on support vector machines?
Assalamu alaikum. I have a small question, if you allow me. Thank you very much for the presentation so far. Just a question, when you talked about the dot product between A and B.
Yes.
If you can go back to that slide. So here, the components of A, which is A1, A2, similar also for B, B1, B2 until Bn. These represents the pixels, each pixel of the picture, right?
Yeah, the intensity values for the pixels.
The intensity value of the pixels, and you are comparing it bitwise, each one with the other one, and then based on
value-wise.
Yeah, value-wise, but each one with the other one, like A1 with B1, A2 with B2.
No, I'm not comparing A1 with A1. I'm just computing the dot product between these 2 vectors.
Oh, okay. And then based on this value, is there a threshold that will say that they are equal or not equal? Or
no, we're just saying that if the number is close to 1 or perfectly 1, then this is ideal. If it's 1, then it's perfect. Then it's perfect. It's perfect similarity, and if it is close to 0, then it's maximum dissimilarity.
The higher the value, the more similar, basically.
Yeah, the more similar.
Okay, is there a threshold normally that is used when you say that they are not similar or they are?
That's very specific to the problem. Right now, we're just using this as how can we decide whether pictures are similar or not similar? Okay.
Yeah, sorry, you don't need a threshold here, because what you do, you're going to compute the dot product, for example, of one image that you want to test or classify against other images. And then you will sort the similarity measures according
and then
to
you will
the,
choose the highest one.
Exactly.
Yeah.
So if you're 3 nearest neighbor, you will choose the highest.
Okay, great. Okay, thank you.
Any other questions? There are no other questions. I will introduce the idea of before the break of SVMs. Let me just open the package. So far we were looking for we have points that were labeled, and we start with a random line, and then going through the points, iterating, we update the line, trying to come up with the best line. Okay, so that was the approach that Perceptron algorithm was using. Now we look into the support vector machines, which also look for separation between the two classes of points, or 3 classes. It depends on how many classes. We start by this. Example by showing the students that we can have more than one arrangement of the points, and we ask which of the 3 boundary lines do you think consider is better as a separator between the 2 camps or the 2 classes. And I think you would agree that, for example, for the situation number 3 is probably the best type of separation. Okay. Notice it's the same. Oh, these are all same points. It says we're just changing the orientation of the line and its location. Okay, so that motivates that although more than one line can work, but we would like to get the best line. We would like to get the best line. Okay, so support vector machines is the tool to find this best line. So the support vector machines finds the maximum margin separator. So this is called maximum margin separator, which is the boundary that maximizes the distance between any of the data points. Okay, and if you look at the figure, we have the dotted lines. These are the lines that are the boundaries now, and we have some data points that are on these lines. Some of these data points are going to be the support vectors. We call them support vectors. Okay, so these points that are on the dotted lines, these are what some of them are called support vectors. These are the points that actually push against the margin. Okay, so we would like to make this margin as wide as possible, but then we hit some of these points, and these points are preventing us from expanding this margin. Like in this example, at least one red point is touching the dotted line, so that would be a support vector. And on the lower dotted line, where it's touching the blue points, maybe one or few of them or more could be a support vector, because these points are the ones that are preventing us from expanding the margin. So with this, we introduce the idea that we are looking for a maximum margin separator. And we introduce the idea that these critical points are called support vectors, because they are the ones that determine how wide this margin is. They are the ones that, if removed, we can extend the margin. Okay, if removed, we can extend the margin. So the support vectors are on both sides of the margin. Now, the maximum margin linear classifier is the linear classifier with the maximum margin that we can obtain for a given data set. We give this example for some data that was plotted, and we show that we can, this is the same data, we can show that we can have small margin, we can have medium margin, and we can have also maximum margin. It depends on how you orient these dotted lines. Of course, the separator that we are after is not the dotted lines. The separator that we are after is this solid yellow line, which is in the middle of these two dotted lines. This is the classifier now, okay? This is the classifier. But in order to find this, we need to find these dotted lines, okay? The ones that are pushing against the data points or the support vectors. So this is on the left, we have an example where we have a small margin, and therefore this is not the support vector machine margin. This is not the maximum linear classifier. But if you go to the one on the right, we orient the lines such that now this is the maximum distance possible between the two dotted lines, or the dotted and the dashed lines. We call them H1 and H2. And where the points are still properly classified, okay? And for this case, this is the largest margin, and the green line would be the line produced by the SVM, the line that would the largest margin classifier, which is the SVM. In addition to this, now on this picture, we are highlighting the points that may be support vectors, and we are highlighting them by circles. So not all points that lie on the line are support vectors. Some of them will be support vectors, and some of them will not be support vectors. The points that are pushing against the boundary, and if removed, the margin would have increased, then these would be support vectors. We go into some small math that has to do with the equations of straight lines in order to compute these lines from the given data, okay? So we give the equations for what would be the equation for H1 line, what would be the equation for H2 line. Of course, these equations for the 2D case, it's just given, or even for the ND, but although the applications or we mostly focus on 2D, but it's the dot product between the W coefficients with X plus B is equal to +1. This would be for H1. And for H2, it would be the dot product of W times X plus B, which is equal to -1. Now, you can see that the margin is the distance between these two parallel lines, which is called D in this case, in this figure. Okay, so the margin is the distance D. Okay, the margin is the distance D. Now, from geometry here, the W vector is always perpendicular to these lines, H1, H0, and H2. These three lines are always parallel to each other, and W is always perpendicular to them. Okay, and not only that, it's always perpendicular to them, but it's also pointing to the points that have are positively labeled. So if you have points that are class 1 and points that are class 0, it's always pointing to the class 1. And from linear algebra, we can prove that the margin D, which is the distance between these two parallel lines, H1 and H2, is related to the norm of W, the magnitude of W, by the formula which is shown. It's equal to, so D is equal to 2 divided by the norm of W. For this part of the course, we need the students to be able to compute these lines and find the separator. We are not interested in proving the formulas, like why would the margin be equal to 2 over norm of W. It's just like to be able to come up with the classifier itself, dealing with straight line equations and solving for unknowns to come up with the coefficients W and the constant B, which determine the lines. Okay. Now, for identification of support vectors, we highlight these facts. So given H1 and H2 that identify a maximum margin, we need to identify the support vectors, which are the, as I said, the points that push against the margin. Okay, so a vector or a data point in this case is considered a support vector if removing it will result in increasing the margin. Okay, now sometimes what may happen is that removing an individual vector, a data point, will not increase the margin, but removing a subset of them will increase it. And therefore, one of these data points or vectors has to be a support vector. Not all of them, but one of them. Okay. We have this example where we give this data and ask the students to determine what is the linear classifier, the SVM, the line H0, the line H1, H2, based on the data. So we have two classes here, points that are labeled -1, and these are the triangles, and points that are labeled 1. And we are asking what's the equation that corresponds to the decision boundary. Okay, so the student has to apply all what we have mentioned before. Of course, the first step is to figure out what are the slopes that are needed to create maximum separation between the lines that pass through the points that are highlighted here in the figure. Okay, and in this figure, I'm drawing this line with different orientations. Okay, we, for example, for the given points here, we know that, for example, the H1 will be pivoted, yani it will be passing through the point 1, 2, because that's the class 1 points, and the H2 line is going to be pivoted or passing through the point 3, 4. What remains is to find what slopes they should have. Taban, they will have the same slope. So we will try to find out what are these slopes. Now we are interested in maximizing the distance. We know that for any 2 points in the Euclidean in the 2D plane, the minimum distance is given by the difference in their x coordinates or the y coordinates, whereas the maximum distance is the distance given by the Euclidean distance between them. Okay, and in this case, we can see that if that the minimum distance here, I think, is 2. You can see that it's 2. Okay, and the maximum distance is given by 2 square root of 2. Okay, which is the Euclidean distance. And from this, okay, from this we can determine that the slopes for these lines is going to be equal to -1, because these lines are going to be perpendicular to the line connecting the 2 points. Okay, and so we put the initial equations for H1 and H2. We know that the margin is given by 2 square root of 2, okay, which can be derived from the coefficients of the straight lines. Okay, and now we are in a position to continue and find out the W coefficients. We find the W coefficients by putting the relation between W1 and W2. We know that the slope is equal to 1, so we know that these things are equal, W1 and W2, and it is perpendicular to the H0, so it is pointing to the class 1 points. We have these 3 equations. We have W1 equal to W2 from what we have learned about W. We have this equation about H1. We have the third equation about H2. So we have 3 equations, 3 unknowns. We can solve for W1, W2, and B. And that completely specifies the entire system. The results are shown in the lower part of the slide. So truly, W is equal to -half, comma -half. This is W1 and W2. The margin is as written before. It's 2 square root of 2, and the equations are as given. And in this example, we highlight that, for example, on line H1, there are 2 points, but only one of them is the support vector. which is the one that passes, this is the one which is 1, 2. Okay, the one which is 0, 3 is not a support vector. Okay, why? Because even if we remove that point, which is 0, 3, this is the maximum margin that we can obtain. Yani removing it will not help us extend the margin. So the margin was not limited by this point. Okay, the margin was not limited by this point. The margin was limited by 0.12. 0.12. Any question on this before? Okay, that's I think I will stop here. It's 10 or 10 on my watch. I'll stop for 15 minutes, and then for the next part, I will continue the rest of the support vector machines, and then also continue with the semi-supervised learning. Any questions that people have on this before I conclude the first part?
Are you looking at the chat?
Excuse me?
If you're looking at the chat, there are some questions.
Chat. Okay.
Yes, please.
Okay.
The questions on the chat, Dr. Ayman already answered them.
Yes, of course. Sorry.
He was answering on the chat.
Okay.
Okay.
Dr. Ashraf, from where we can get this material?
It's on the Blackboard.
Oh, we can get it in a Blackboard, huh?
Yes, it's all posted on the Blackboard in PowerPoint format.
Okay.
And also the notebooks are posted there.
Okay, I look on the link, they have it somewhere, but this particular material, when you show us some of the examples, it is directly from the, what do you call it? The collab?
No, the notebooks as well as the slides. They are on.
I'm saying the access the collab on Google.
Yeah, but we don't access the collab. You access the notebooks themselves. They are posted on Blackboard, and when you go to your collab, if you have a Google account, you just upload it to your collabs.
Oh, okay. Okay, thank you.
I shared the material also in the chat here, based on the request or something.
Yeah, I saw that. Thank you.
Ashraf, can we ask a question?
Tafadhal.
Thank you very much for the presentation, very informative. I just want to ask about how students find the course. Because so far it's very interesting, to me at least. The math is not complicated. So can you give us some idea about
I'll give you my input on this, and then Dr. Ayman will give you his input because he taught it for more times than I did.
Yeah.
I think it is on the reasonable to a little bit heavy side. That's my take on this, especially that what we are covering here in this workshop is about 50%, almost roughly. There is another 50%, and this one is compressed a little bit. There is also the non-classical part about propositional logic and goal trees and search algorithms, constraint satisfaction problems. It's very well rounded. It's excellent content, but I think like at least for the summer that we did this summer, I find it tight, very tight. But as you said, there is not much complicated math in there. But there are a lot of details.
Okay, let me give my input. Let me give my feedback on this question. Actually, the students, in terms of concepts, I think they are doing well. They're grasping the concepts and so on.
And they like it.
Yeah, they like it and they love it. The problem that we feel some of them are facing or complaining about is the programming aspects. They keep saying that computing majors have advantage over us, and we tell them it's not true. Like you take Python course as they do, you take the data science as they do, and when you come here, and we don't really give them heavy programming, it's just like notebooks. We give them notebooks and we show them how to do it, and then we ask them to do like a homework similar to that with different data sets and so on. But some of them convince themselves that they cannot do programming. Like, I am business, I cannot do programming. I am chemical engineering, I cannot do programming. But this is like the weak students. However, really the excellent students, I mean, I had in my class the best students from mechanical engineering, for example, and he was doing the best like in programming and so on. So it's not really, I think it's gonna take time until some of them really get convinced that yes, because some of them, they just don't want to learn basically. And that's the problem. We try to motivate them and convince them and help them. We tell them, okay, you can ask us. We work in groups of 2 and so on, so that they learn from each other, collaborative learning and so on. But overall, I would say that we've received comments last year when we improved the material that this is the best course out of the 3 because they see finally the benefit after they're taking the sequence of 3 courses. You see the application of it and so on. So far, I think we have positive feedback.
Yeah, Assalamu alaikum.
Salam.
Yeah, thank you, Dr. Ashraf, for the nice presentation. A quick question, please. It's not clear to me how you decided that the 0.03 is not affecting the margin. You decided that based on numbers or what?
No, it's just by looking at the geometry of this 2D plane points. If you remove this 0.3 point, the distance between the 2 lines that are drawn cannot be increased further than what it is now. Can you?
Yeah, but if we rotate the line, the distance will be different.
Yes, but this is the maximum distance that we are at. It will be less, but this is the maximum now. So it so happened that the maximum now we have is not affected by this 0.3.
To clarify the point to you, consider removing the point 1 and 2.
Yes.
Now, what will be the maximum margin?
It will change, I believe.
Yeah, it will become 3. Now you can have vertical lines to draw the decision boundaries, and it will become 3. So that's why 1 and 2 is a support vector, because if you remove it, it's going to increase the margin.
You are going to increase the margin.
However, the other point, if you increase it, no matter what you do, you will not get higher margin than this. So that's why it's not support.
Thank you very much.
Okay. It will be clarified with the second example also. Okay. Any other questions? I will stop for 15 minutes and come back, inshallah. Thank you very much. السلام عليكم. كيف حالك؟ Can you send James again, please? Thank you. So أنا تعبتك معي. Okay. we start?
Yes.
Bismillah, alhamdulillah, salatu wassalamu ala rasulullah. I have shared the PowerPoint slides for the 3 parts on the chat. I have uploaded them. As I said, they are already also available on the Blackboard, which is for this workshop. Okay. So we finished last time by introducing the idea of support vector machines and the trying to find what is the maximum margin classifier between that separates between the labeled points. Okay, and we gave also a numerical example of how to compute these lines and how to determine which data points or support which points are support vectors and which are not. Okay. Now we go into the idea of hard versus soft margin. We introduce or motivate this idea by this very simple example. We have an example of some training points which look like this. Let me just go. Okay, which looks like this. So we have a data that is coming from some experiments on weight of mice. And the red points are, the red dots represent mice that are not obese. Okay, whereas the green points represent mice that are obese. And we would like to find a classifier that suits this data. So to classify a new mouse, whether it's obese or not, we would like to define the threshold. Now, based on what we have studied before, if we want to look at the maximum margin classifier, we look at the 2 endpoints from the either side and determine what the margin should be, which is looking at the maximum margin classifier between these 2 points. For this very simple case, it's very clear that we can put one line on this last red point here and one line on this last green point here, and the distance between them would be the maximum margin that we can have between these 2 sets of data. Okay. Now, if we have data that looks like this now, so it's roughly the same data as before, except that the red points where the mice are not obese, they have one outlier. And this outlier happens to be very close to the green points. Okay. Now, if we apply the same rules that we done before, it means that the margin between the not obese and the obese will be very tight. And the classifier will be where this brown line is located. Okay. And this is because of this new added outlier here, the red point. Okay. So the outlier node is classified as not obese because it lies it's classified because it's much meaning here the outlier is not an obese point, but it is very close to the points that are all classified as obese. Okay, so this motivates us to for example, even if you bring a new point now, which is like this black point, and you want to classify it, it is to the left of the line, which means it should be classified as not obese, but it is also very close to the green points, which means logically it should be classified as obese. And this is all due to the fact that we have computed the margin based on taking into account that outlier. Okay. So the maximum margin classifier that we computed is very sensitive to the outliers. So what can we do about this? What we can do is we would allow the so what we will do is we will allow to put the margin, the classifier, which is the brown line, and allow some misclassification. For example, here we have decided to put this brown line somewhere here in the middle, although we know that it is going to misclassify this red point. So this outlier is going to be misclassified. So in all the examples before, the boundary that was created for the SVM or the perceptron, we would like it to have zero misclassification. But right now, because of this outlier, we are willing to accept that there are some misclassified points, and the margin now is called soft. Okay, this is not the typical hard margin for an SVM machine. Okay, so we are going. So some misclassification will happen during the data. And to determine what is the best soft margin, we are going to use a procedure which is called cross-validation. This is explained a little bit down the road. Okay. And since we allowed some misclassification in this point, the red point is clearly misclassified, we are going to call this as a soft margin. When we use this soft margin to classify the data, we refer to the system as support vector classifier. Support vector classifier. Okay. Now, this is again a reiteration of the point that we discussed or mentioned when we talked about the perceptron before, is that the decision boundary that we're looking at is always one dimension lower than the number of dimensions in the features. For example, if we have features that lie along a line, like for example, in the previous example where it's weight of mice, then the separator or the classifier is a point, it's a dot, okay, which has a 0 dimension, okay? But if you have points that are in 2D, and we have two features, x1 and x2, then the separator is a line. And if it's in 3D, then the separator is in is a plane, or it's 2D, and so on, okay? Now, after finishing this idea, which is hard versus soft, we go into the point of linear separability and the idea of kernels. Okay, we motivate the idea by showing these three different types of data sets, and we see that the first two are linearly separable, and therefore you can find a line, and it remains to find what is the best line, but there is a line definitely. If you go to the lower two, you can see that there is no line that can actually separate between the two groups of data. Okay, so straight lines will not work for the two cases that are below. Okay, so we would like to find a separator, and of course in this case, for the two cases that are below, this separator will not be a straight line. Okay, but we have already said that the separator can be of any dimension. It depends on the dimension of the features. Then what we can do is we can increase the dimensionality of the data, which would allow us to find a separator which is not a straight line, and then we can project it back to the number of dimensions that we have. And with this, we use this example. This is a very nice example that introduced the kernel trick, which is the idea of using kernels for support vector machines. We are given data as shown in this figure. This figure shows the data of a drug dosage that is given to patients. Okay. Now, you can see from the graph, if the drug dosage is very low, which is like this is the dosage in milligrams. If the drug dosage is very low, the patient is not cured. And this is shown by the dots that are red to the left side, okay? And you can also see that if the drug dosage is very high, like 3.5 milligrams and above, also the patient is not cured. The patient is cured only for these green dots, where the drug dose is anywhere between 2 to 3 milligrams, okay? Now we would like to use SVM to classify a drug dose. If we give a certain drug dose, what would it be? Cure or not cure of the patient? Okay. Looking at the data itself as it is here, you can see that it does not, a linear separator does not work perfectly. So how can we classify these points? Okay. So one way to do it is to actually transform the problem into a higher dimension. So in this case, we map the data from X to X squared. Okay, we map the data from X to X squared. So you can see now on the graph that is shown is that the data is being plotted dosage versus dosage square. Okay, and now it's looking, when you look at this 2D plot now rather than the 1D plot, you can draw a line that separates between the red dots and the green dots. This was not possible when the data was on one dimension. Now it is possible when the data has been transformed to 2 dimensions. Okay, and the transformation here happened with a simple polynomial x squared. Okay, so we can now draw a support vector classifier to classify the data, and this will help us classify the groups of people who got cured and those who did not get cured. Okay.
Quick question, Doctor.
Yes.
So that choosing this transformation x squared, is it arbitrary or is it?
Yeah,
how
we
did
don't
you choose it?
we just in this course we just tell them that you can choose nonlinear functions like mainly polynomials and radial functions. These are options also in the Python code. We don't go into the math behind it.
Okay, I see.
It's based on trial and error. You choose which one that gives you the minimum classification error.
Oh, okay, I see. Actually, this brings me also to another question is, you kind of answer it, which is to which extent do you go into explaining the mathematics behind the
We
equations?
don't. No, we show how it works.
Yeah.
And there is, we only show, for example, for the kernel trick
I know that the
transformation,
SVM, the mathematics behind it can be very complicated, actually.
it's an optimization problem. We don't go into that at all.
Okay, I see.
Yeah, we don't.
Yeah, assalamu alaikum.
Walaikum salam.
Yeah, Dr. Ashraf, can you get back, please, to the previous slide? Here, as you said, it's a one-dimensional, maybe, data, and the margin will be dot, as you said. So why don't we use dot between the two dots as a margins? Can we use it?
Well, the SVM is deciding on a one decision boundary.
Okay.
So we would like to find that one decision boundary.
Okay.
That separates between the two classes.
Okay, thank you.
So this is the summary of the idea. Is when we are given a set of non-linearly separable points, like on the number 1 here, we are shown points that are non-linearly separable. What we can do is we can transform them using a kernel, which is basically a nonlinear function in the form of x to the some power, or radial functions, which involves an e to the some powers. And after doing that, we can find the plane that separates the points. And when we find that plane, we project it back to the original space. In the original space, that classifier will not look like a line anymore, or a plane. It will look like like, for example, this circle that is circling the colored points. Okay, this is the kernel trick that. Okay, and there is, as you said, for this material specifically, they try it using the Python by, as I said, options in the Python code. They don't have to go for the calculations themselves or the math behind it. Okay. Finally, we finish with the advantages of SVMs. So regularization capabilities, the SVMs has good generalization capability, which prevent them from overfitting. We will talk about overfitting in a short while. They can handle nonlinear data efficiency. They can use the kernel trick, as we have discussed. Okay, they are stable in the sense that small changes in the data generally do not greatly affect the hyperplane or the boundary that was found or calculated, and hence the SVMs, okay, are stable. So the SVMs is stable, okay, and they are optimal. The nature of the problem and the computation, especially when looking for this margin, and so the respective support vectors is convex optimization in nature, which helps finding the global best model for these kinds of problems. Okay. Before I go to I will the final part of this package, which is about how to evaluate the decision boundary itself. I would like to show the notebook on the SVM. Okay. As I said, these notebooks, they are already shared on Blackboard, and we will upload them also to this chat as well. So this is the last. This is the notebook on SVM implementation. Let me just go up. Is it shared? Not shared?
No.
Okay, because I'm not sharing the screen. Stop share, and I will share the. Okay. So this is a simple notebook on recipes that are made to either cook a cupcake or cook a muffin. Okay. I don't know where did this come from, but this is the notebook or the example that we have associated with this material. Okay. So the data set itself is not very long. It's about 20 data points. First of all, we import the classes that are relevant to this exercise. Okay, we execute them, and then we show the data points. These are the data points. These are the, let me just connect. So as you can see, the data itself is about 20 points from 0 to 19, and we have these ingredients: flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. And the type is either 0 or 1. One of the types is for cupcakes, and the other one is for muffin. And the idea is, can we build a machine that would, given some ingredients, would recognize this is a cupcake or a muffin? And in this exercise, he's going to use SVMs. So initially, we plot the data, and we show that it looks like it's linearly separable. And we have type 0 shown by red points, and type 1 is showed by the blue points. And he's plotting using 2 features only, because we want to show the graph. So it's sugar versus flour. So only these 2 features. Okay. Now he uses these 2 features, and he uses, in this case, he just makes the ingredients only these 2 features, and takes the label as whether it's type 1 or 0. Okay. And he calls the SVM classifier, support vector classifier. He creates the model, and then he fits the model given the ingredients and the labels that he has. Okay. And the results are given. He's going to visualize the results here in this few lines of code where he plots the line. So he uses the coefficients that were computed using the SVM. Okay. And he plots the line to show that the line indeed separates between the 2 points, which is the case. Yes, the line separates between the two types of points, which is the class 0 and class 1. Now, just as a note, this line may look like it has a slope, but this line is almost vertical. The y-axis is actually very large compared to the x-axis. So this line is actually almost vertical. Okay. In the subsequent parts of the code, he plots the H1 and H2 lines based on the math that we explained in the slides. Okay, because we have already found the coefficients W and we know what's the B constant, so we can find the equations for H1 and H0, and these are the two lines are plotted here with the main decision boundary in between. Okay, and then in the rest of the code, he's gonna predict new cases. So he's gonna pass some information, like for example here, he's passing in this line here, he's passing flour and sugar quantities 50, 20, and he's asking what would be the classification. So he's gonna pass this. Okay, so let me just define this. Then he's passed this, and we'll ask for the prediction. Okay, and then we will plot it. And this point will come up to be, okay, this is the point that he was asking for, which is 50, 20, and it is being classified as type 0. Okay, it's being classified as type 0. So type 0 here is a muffin, so he's making a muffin recipe. Okay. And the set continues by giving different quantities of these ingredients, like 40, 20, and things like that. So this is basically the notebook on SVMs. At the end, we evaluate the entire model. Remember, we have 20 points. We separate them into 16 for training and 4 for testing. And we evaluate the model based on the 4 points, and we got these precision, recall, and F1 scores, and this is the corresponding confusion matrix, which is going to be the subject of the next part of this session, is what do these numbers mean, and how do we evaluate a specific decision boundary that we have came up with. Okay. Any question in general about SVMs before we leave, because we're done with SVMs. Okay, I will stop sharing this notebook, and I will go back to share the material. Okay, so. So now what we are trying to do here is we have data, we have computed a line like this yellow line, which separates the data and allow us to use a classifier. Now we want to evaluate how good of a classifier is this. So the first thing we do is we define a loss function, okay? So this loss function is going to help us to tell how poor or good this classifier is doing, okay? For example, for the same data points, this loss function should give me a 0 if the actual is equal to the predicted. So you can see that now on the points that are, most of the points on the graph they have 0 in them. It means they are correctly classified, okay? They are correctly classified. This is not the class, this is the loss function value, okay? The loss function is 0 when the classification is correct. Okay, so the actual label is the same as the predicted label. And there are only, in this graph, we can see that there are 4 points, 2 blue, 2 red. They have 1 in them. So the loss function is equal to 1. For the two blue ones, it's equal to 1. And also for the two red ones which are below the line, it's equal to 1. This is the value of the loss function. Now, the objective is, when you are designing these lines, you have to minimize this loss. You have to minimize this loss. Okay. Now, we define the points as follows. We define the points are true positive. These points are labeled as 1 and predicted as 1. So we call them true positives. Okay, true positives. And in this case, for example, given this figure that we have, if you count the red, the blue is the label 1. We have 14 points in the blue. They are correctly classified. That's why here we have 14. Okay, we have here 14. Okay, which is the true positives. On the other side, we have also red points that are correctly classified, and these are negatively labeled. So the original label is 0, and they are predicted as 0. So these are true negatives, and we have 12 of them. So this gives us this number here. Okay, this gives us this number here. Okay. Okay. Now, in between, we have 2 points that are negatively labeled, like these red points. These are negatively labeled points, but they are positively they are classified as 1s. Okay, they are classified as 1s. So these are false positives. Okay, these are false positives. Okay, so these are false positives here. So the correct label is 0, but they are labeled as 1. So these are false positives. And also we have, sorry, in the other side, we have also points that are labeled, originally have a label of 1, but they are predicted as 0s, which are the blue ones. And these are false negatives. These are false negatives. So examples should have been labeled as 1, but they were labeled as 0. Okay. Now, this is the confusion matrix. And in the codes that we have shown so far, the students can call the proper methods to evaluate the decision boundary that they have created in the model. And the confusion matrix will be computed for them automatically. The confusion matrix that we are showing in this slide is 2D, like we have 2 classes, it's 2 by 2. But you've seen in the first notebook, it was like 3 by 3 because we have 3 types of the iris flower. And I think in the programming assignment, we gave them 6 types of dates. So that the confusion matrix was 6 by 6 and so on. So we generalize it in the practical examples that are given to the students. Now, in order to evaluate, the previous one was just the confusion matrix, but then we look at other basic metrics that could be used to evaluate the model itself. On the right here, we have a list of these metrics. In the slides, we focus on the first 3. So it is the accuracy, which is given by the formula that is shown, and then the precision, which is given by the formula shown, and also the recall. And we focus on when do we use each of these metrics and for what scenario these metrics are appropriate, and for what scenario these metrics are not appropriate, because they differ in their use. The models, the codes that we showed, it will give all these metrics for the problem, but it's up to the students to pick the ones that are more relevant depending on the data set and the scenario that they are utilizing. For example, here we're saying that the accuracy measure is not good when the data is imbalanced. Okay, because the accuracy measure is taking the true positives and true negatives divided by everything else, which is true positives plus true negatives plus false positives plus false negatives. So this one here is not good measure when the data is imbalanced. Okay, and we are giving here an example that consider data 100 data points that we're taking from flight records. And these 90 points of these 100 points, it's about a pilot landing a plane. If the pilot lands the plane safely, we consider this a positive sample. Okay, and if it crashes, la samhallah, then we call this there are 10 points like this, and we call this a negative sample. Now, if this machine learning algorithm that we build correctly classifies all the positive samples, yani all the ones that are landing safely will be correctly classified, but all the negatively labeled samples are wrongly classified. Yani they are considered as false positives. Then this means that my true positive is 90 and my true negatives are 0 and false positives are 10. If you compute the accuracy for this model, although it has failed to predict any of the crashing samples, it still has an accuracy of 90%. So it's kind of misleading. Yani the accuracy is high, but it has failed to predict any of the failing scenarios. Okay, and in this case, the accuracy is not a good measure. And then we move on to the precision and the recall and the other ones. So, for example, for the recall, we say that this is a much better measure than precision when false negatives are important. Whenever you have a scenario where false negatives are important, then the recall is much better, because the formula for recall, you can see that it has the false negatives in the denominator. Okay, it has it in the denominator. So the computation of the recall will be affected by the false negatives. And we give this example. Okay, for example, if we have مثلا a rare cancer data modeling, positive samples where you say that there is a cancer exists, and the negative samples where you say that the cancer does not exist. Then when you say that there are false negatives, it means these are cases where cancer exists, but they were identified as no cancer, which is a very critical issue in this scenario. So for this scenario, when there are a cancer exists, but you say that it does not exist, the false negatives are very important. And therefore, the recall would be a better measure to characterize the decision boundary that we have created. Now, on the other hand, if the false negatives are not important, and we give here as a very simple example of YouTube recommendations, the precision would be a much better metric. Okay, for example, here we're saying let's assume that the positive samples is this video should be recommended, and the negative sample is that this video should not be recommended. Now, if you say false negatives, it means that the video should be recommended. The video that was supposedly should be recommended ended up not being recommended. It's not a critical issue, and it's not very bad. It's not that bad relative to the previous case, and therefore the precision in this case would be more appropriate. This is how to evaluate it. Okay. Now we look at the issue of cross-validation and the training versus testing. Okay, in all the models that I've shown before, starting from KNN, the perceptron, and SVM, whenever we build the model, after we build the model, we train it on some part of the data. If you go back to that previous codes, we split the data into training part and testing part. Okay. So we want to estimate the parameters of the model. In our case, for example, in the perceptron or in the SVM, we want to estimate the W's, that make the decision, the boundary. So estimating these parameters of the machine learning model, we want to guess the shape of it. We want to estimate it based on this is called training, and we will use the training points to do that. But when we come up to evaluate the performance of that model, we will do it. This is called testing, okay? And this testing should be done on a set of data preferably that has never been used or seen before. Okay, so we have two things to do. We have to do the training, in which we estimate the parameters for the model, and then we evaluate the model, which is we call testing, and this should be done on a set of data that has not been seen before. Okay, so what to do? What to do is to split the data, as we've seen in the split method that was shown in almost all the codes. Okay, so we split the data. We divide the collected labeled data into training set and testing set, as seen in this figure. Okay, a common practice is to allocate maybe 80%, 75% of the data as training, and the remaining 25 or 20% as for testing. This is called the holdout method. Okay, and the question becomes now is which 25 or percent of the data to choose. Okay, now in order to overcome this point, there is a procedure. Is we do the k-fold cross-validation. For the k-fold cross-validation, we divide the data set into k equally sized subset, as shown in this figure. Okay, and we train the machine learning algorithm on k-1 subsets. These are my training sets. And then I will evaluate the model on the one set that is remaining. Now I will do this k times because I'm going to change where the location or the test set itself. And then to get the final performance of the machine learning algorithm, I'm going to average the error performance or the performance that I want over all the k validation sets that I've done. This is generally the procedure that is followed in k-fold cross-validation method. We are giving here an example where we have the data is being split to four folds, to four-fold, 1, 2, 3, and 4. So we are listing what are we training the data on and what we are testing the data on, what we are training the model on and what we are testing for. So we're doing 1, 2, 3 as training and then 4 as testing. In the second round, we do 1, 2, 4, and the set 3 is used for testing. And then 1, 3, 4, and then 2 is used for testing, and then 2, 3, 4, and 1 is used for testing. Now, in practice, as the slide shows, that it's common to use a 10-fold cross-validation. And this is all programmable in the codes that were explained before. It's a parameter that could be passed to the method, which you can control what is the value for k that is desired. Now, what are the advantages and disadvantages of this approach? It's that the k-fold cross-validation can help us to obtain reliable estimates of the model generalized performance, meaning you find its performance on unseen data, okay? Because if you do it for the data that it was trained on, it means this is not going to be the true performance of the model. And the main disadvantage is that it is computationally expensive because you are going to going to repeat the computations k times. Okay. Now, the last point on this part is overfitting versus underfitting. So far, we are coming up with a decision boundary. Okay, and let's now look at this problem from another perspective, whether it's underfitting or overfitting. Given this data that we are showing on the graph, we have red circles and we have blue circles. How can we train the model and obtain the best classifier? Okay, now the first idea that comes to mind is look for a linear classifier. And it's clear in this graph or this for the given data set is that the data is complex such that a linear classifier, which is a straight line, is not really suitable for this case because there is a lot of overlap between the blue points and the red points, okay? So no matter how you rotate this line or shift it up, down, or change its slope, you will have high misclassifications, okay? So this is a case of underfitting. So we say that this decision boundary, which is the simple line in this case, is underfitting. And it's actually oversimplifying the complexity of the data. It's not appropriate given the complexity of the data. So the idea number 2 is to actually look for a curvy, wavy kind of border, okay, between the two camps of points, red and blue. So to follow our procedure about splitting the points between training and testing, so let's split them into two parts. The one on the left is the one used for training, and the one on the right is the one used for testing. And we will try to come up with the decision model boundary and the model based on our training set. And for that, let's assume we are able to, and we can obtain this very wavy curve, which provides 0 misclassifications for the training data. Okay, so this decision boundary fits all the points in the training set as shown, and there are 0 misclassifications. But now when we go and apply this on the training, on the test data itself, the set that we put aside to test our model, we can see that we have a lot of errors, a lot of misclassifications. Okay, and the reason for that is that this line was overfitting the data. This line was overfitting. Okay. So what is the solution? The solution is we want to allow for misclassification, and we get a line that does not overfit and does not underfit. Like, for example, the almost like a semicircle line that is shown has some misclassification, but it's not underfitting. It's not a straight line, and it's not a very wavy line. And therefore this is considered a good compromise. Okay, so this is usually determined by the acceptable range of misclassifications. When the k-fold algorithm is running, it's evaluating these misclassifications for every iteration, and we try to pick the one which is has the lowest number of misclassification on the unseen data, of course. Okay. Now, this concludes all the material on supervised learning, which is KNN, perceptron, and SVMs. Okay. Any questions? Because what remains is unsupervised.
A quick question. So for the evaluation, I noticed that most of what you're talking about is classification. Do you teach the students also about regression when the label is numerical value? No. Okay.
No. It's classification.
Okay.
They covered regression in the previous course.
I think it's 291.
Yeah.
Okay. The ISC.
Yeah.
Yes.
Any other question?
Yes, Assalamu alaikum.
Salam.
Thank you very much for the nice presentation. One question regarding the overfitting and underfitting. Usually, if there is overfitting, usually what you do or how to overcome this issue?
You're asking me?
No, yes. According to my knowledge, we reduce the number of features, and maybe we will get less, or the issue of overfitting will be much less.
No, it's not like that.
This is handled by deep learning when you drop out and turn off some of the nodes. That will be talked about by Professor Ayman in the second session.
Okay, I see. Okay.
Yeah, there are ways to techniques that get used to avoid overfitting when training. The general one is you split your data into training data and validation data and testing data. So while you train, you measure the accuracy of the validation data. And if you start seeing that the accuracy of the training data is increasing while the validation data drops, you know that, okay, you are entering into the region of overfitting. And then after certain threshold function, you could stop. So you stop training because you know that it's not performing well on data that it hasn't seen, which is the validation data. So this is usually the technique used. in general, but for certain models, there are other techniques that can be used also to avoid overfitting. Specifically.
So this technique for overfitting and underfitting both.
Yeah, underfitting, Manado, your model is not giving you high accuracy for the training data.
Yes.
So that's underfitting.
So underfitting, you start to increase the number of faults, or you keep running.
If you have underfitting, that means you need to increase your training data.
Yes, I see.
To increase that.
Statistics, what you do, we increase the number of features, if possible.
Maybe number of features, maybe number of training data. Like if you're increasing the number of samples, it's not helping. That means you need to increase the number of features.
I see. Okay. Thank you very much.
Okay. So we move to the last part of the presentation. So this part is about unsupervised and semi-supervised, the part that is covered in 292. Okay. Part of this, by the way, especially when we talk about unsupervised. So unsupervised meaning we deal with the problem as a clustering problem, and that I think was covered in ISE 291. In this course, we focus mainly on k-means algorithm. Okay. And for the semi-supervised, we give them an introduction to reinforcement learning, and specifically this Q-learning algorithm, where we build a Q function that allows us to estimate the reward from a given state given some actions. Okay, so we start with unsupervised. So for the unsupervised learning, we have data, and now we don't have labels. The data itself is not labeled, and we don't give feedback. And the AI or the machine has to learn patterns from the data itself, okay, without any feedback being given. Okay, that's the essence of being unsupervised. Okay, so in the previous three methods that we give before, the data when we train on it was always labeled, so that was considered as a feedback to the AI algorithm. Now we don't have it. So this is the figure here is showing unlabeled data. As for us, we're looking at this data. You can think of patterns from this data. You can see that there are three natural clusters, for example, that maybe put for the data, or the data itself could be arranged into three natural clusters, at least for this specific example. Okay. So that's where the clustering problem comes into. So we want to organize the set of objects into groups into such a way that similar objects fall in the same group. That's called clustering. Okay, similar objects will fall in the same group. And some of the clustering applications that will be highlighted in the class, for example, is marketing research, image segmentation, medical imaging, social network analysis, and genetic research, and other applications as well. Okay, focusing on the k-means clustering, the algorithm itself will divide all our data into k different clusters. Okay, k different clusters. The clustering data is based on repeatedly assigning points to the clusters. Yani, for example, we will assume we have k, and then we will look at these points, to which cluster do they belong to? And we will do that iteratively and start to update this. Okay. Now, deciding on how many clusters to start with, it's usually this number is unknown. So this requires experimentation. Like for this very simple example that we have, k equal to 3 looks very natural. Okay. But it could be clustered with 2, or it could be clustered with 4 as well. Okay. So k is a parameter indicating the number of clusters, and usually this is unknown and requires some experimentation. For this specific example that we give to the student in the slides, we start with 3 clusters and we locate them randomly in the shown point. So we have one blue, this is the cluster center, and there is another one red, and there is another one green. Okay, and then we want to classify the points based on these. So what we do is we compute distances. Okay, so the 3 centers are indicated as shown, and the center of the clusters represent the mean of the cluster. So we would like now to compute which points are closer to the blue. We will label them as blue. Which points are closer to the red, we would label them as red. And then which points are closer to the green, and we will label them as green. And this is the initial now the labeling of the points, okay, based on the clusterings that we have. Okay, now this is the first assignment. Okay, so this is the initial clusters based on the first initial random centers that were given at the beginning of the problem. Now, how can we improve? We can improve by recomputing the centers or the means of the clusters. Yani the points that were deemed as blue, okay, now we compute their center. And that gives us the new location of the centroid for that blue group. We do the same for the red points. So all the points that were labeled as red, we compute their center, and that becomes the centroid for the red points. And we repeat that for the green. And now we have this, okay? We have the new scenario, which is shown in the figure. And then what we do is we go and iterate again. We go through all the points, and the ones that are close to the new centroid, the blue centroid, we label them as blue. And the ones that are closest to the red centroid that was computed in the last step, we label them as red. And the ones that are closest to the green, we label them as green. And that gives us new clusters. And again, we go and compute the new cluster centers. And we iterate until we don't observe any change in the location of the centroids. That means that the problem has converged. Okay, the problem has converged, and we have computed the final centroid for these data sets that are given to us. Okay, this is the k-means in short, and we have demos. I want to show the demo. Okay, let me just I want to open this. You can see this, right? The web page, which says what kind of data you would like.
Yes.
Yes.
So, for example, if I choose the random data like this, and we add centroids, 1, 2, 3. The centroids are added randomly. Each time you add a centroid, all the points are being classified as either to that or that label, or that group or the other group. And okay, let's assume I want 4. So this one is 4, for example. So I have 4. Now we can start doing go, which means it's going to start to update the centroids based on the points that were colored. And each time we update, a new center of points is being created. And you can keep doing this, pressing this, and the center is updated until it converges. Now we show that for many arrangements. This is one of the very difficult arrangements of points. There are many other arrangements that this tool allows us to. And in this, the student can see how the center of these clusters keeps changing and finally converges. How difficult it is with certain number of centers. How easy it is with certain number of centers. It depends on the configuration of the original points. We have this tool, and we have another one which is also being shared in the slides. Let me just take this out. Okay, so we have the first tool here, which I have this figure is coming from it, and then the second tool where the second figure is coming from this. These are very nice tools that we use to demonstrate the k-means problem and the way it works and how the centers are being computed and how does it converge eventually to the final centers of these clusters. Okay, so this finishes the k-means, and now we come to the reinforcement learning or the semi-supervised learning. Now, for the unsupervised k-means, the data was completely unlabeled, and the AI was trying to find a pattern given the data points alone. For this one here, it's called semi-supervised because we are aiding the AI. We are giving it some information. This information is the reward, okay, or the punishment. So the AI is it's not fully unsupervised. It has some supervision by giving this a reward or a punishment for every action that it takes. Okay, so imagine that so the AI here, or the AI agent, or being a robot or a program, is going to learn from experience. So we have an agent, which can be a program or a robot. This agent is going to interact with its environment. It's going to do some actions. And when it takes an action, the agent moves from one state to another. Okay. Now, for every action, we assign a reward or a punishment. Okay. Now, the agent learns what to do and what not to do in the future actions based on the rewards that it is seeing. Based on the rewards that it is seeing. So you can see that we have an agent. The agent takes an action, and that action makes some change in the environment, which makes it change its state from one state to another, and there is a reward associated with that action. A very good place for this application for this reinforcement learning is for robots and droids, where they have to climb a stair, for example. If the robot manages to climb the stair correctly or do a step correctly, then it rewards itself and it knows that it has to repeat this again. But if it falls, then it means it's not gonna try to avoid this action again in the future. Now, the math behind this reinforcement, we briefly introduce it. We don't go into the details of this. We say that this is basically a Markov decision process, okay, which is a formal model or to make a decision making, representing states, actions, and rewards. And we show this graph of states. We have a state which has, there are 3 different actions coming out of this initial state, leading to 3 different states. Each is associated with a reward. And then we start by putting just the definitions. So we have a set of states S, okay? So we have a set of states S. These are all the circles. And then we have actions of S. So for every state, there are some actions that apply to that state, okay? There are some actions that apply to that state. And these are the arrows. So every state has some arrows going out of it. And these arrows represent the possible actions from that particular state. Now, for generality, there is a transition model, which is the probability of going from state S to S prime if you take that action A. Okay, so that's in general. So if you are in state S and you take some action A, there is a probability that you go to a state S prime, and that is defined by this transition model, which is this probability transition matrix, capital P. Okay, although we will not touch on this later on. Actually, the model is deterministic later, but in general, this is the case. And the reward function, which is very important, R, is the reward of going from S to state S prime if we take that action A. Okay, and this is the input that we provide to the AI. Okay, we assign reward numbers for the actions of moving from one state to another. Okay. We give this very simple example of a world of 4x5 navigation problem for a robot. So we have 4 squares by 5 squares. This robot must navigate this maze, and the robot is this yellow circle. Now the green is the goal. We would like it to reach there. And the red rooms are the bad places. If maybe it's a pit or something, if it reaches there, it gets a punishment. But if it gets to the green, it gets a reward. Okay. So this is the world that this robot must learn how to navigate and reach the goal at the end. Now, for this particular world, there are the actions that it can be taken for in a given square are either move right or move left or move up or move down. These are the actions depending on what cell the robot is in. But these are, in general, these are all the 4 actions that it can do. Okay. Now, some actions are bad because they may land the robot in the bad place, the bad room, the red one. Some actions are good because, like for example, if he's near the goal room and he takes an action to go up, then it will land in the green square, and that would be good. Okay. So we would like to build a function or a matrix called Q. That Q matrix will guide how does the robot makes its decisions. So this Q matrix, it will, for a given S, if I take a certain action, what is my expected reward? Okay, so this Q learning method is a method for learning this function, which is Q of S comma A, which represents my reward value for performing an action A in state A, S. This is different than the R matrix that we talked about here. This R is different. This R is the immediate reward that I, as a programmer, assign to taking an action A from S that takes me to S prime. Okay, this is my feedback into the code, the algorithm. But what I want to compute eventually is this Q matrix. This Q matrix is the value, is the estimate of the reward of the value of performing an action A in state S. So initially, this matrix is not known, and we don't know it. So we actually have it all zeros. Okay. Then we let the AI play based on the immediate rewards it gets. And when it reaches the final goal, it rewards itself. It updates these entries in the Q matrix. And if it does this a large number of times, then the build of this matrix converges. And then it can use this matrix to make the decisions. So there is this stage of first trying to learn, which is building this Q of S comma A. And then after it learns this matrix, it can use it to navigate. It can use it to navigate. So initially, this Q learning starts as follows. We start with Q being initialized to zeros for all the states, for all the actions. Then when we take an action and we receive a reward, we make estimate of this QSA. Okay? And we update it in the matrix. Okay. And then we play again. And we keep updating the entries. Hopefully we update all the entries of QSA. And then if we do that large number of times, then this Q, the structure of this matrix will converge. And then later on, we can use that for making decisions. Now, to do the update and the Q learning, we follow this rule. So we start with Q of SA comma equals 0 for all the states and the actions. Every time we take an action A in state S, we observe the reward, the immediate reward R, which is obtained from the R matrix. This is always specified. And we make the following. The new entry in the matrix is equal to the old entry plus alpha of the new value of estimate minus the old value estimate. Okay. So alpha A here is the learning rate. Okay. It shows how much we rely on the new versus the old. This is, as I will show in the next slide, this is exponentially weighted averaging. So we're trying to update this Q of SA based on the what was the value before, which is the old QSA, and based on what we think the new one is. Okay, so so this equation here, okay, and alpha is the exponentially weighting averaging parameter. We take this as between 0 and 1. It basically controls how Q function is updated and how fast do we do that and how much do we rely on old versus the new estimates. Okay, now so we can write actually, as you can see in the second line here, Q of S is equal to 1 minus alpha times the old QS plus alpha times the new one. So this is where I said that it's exponentially weighing the old estimate of Q versus the new estimate of the Q. Okay, so now we go further into defining how to compute this new value estimate. We know that if I take this action action A from state S, I will be receiving a reward. So part of my new estimate value is R. So I have R plus the future reward. This future reward will depend on where do I land after I move from S with the action A. Okay, so this new value estimate is going to be R, which is taken from the matrix. This is the immediate reward. It's specified. There is no randomness in there. And then I have to look for, if I take that action A in state S, I move to some state, what is the new estimate in that new state? And for that, it's written this way. So again, the final update is going to be equal to the following. Q of SA is equal to Q, the old QSA plus alpha, which is the learning rate, times this quantity. This quantity between the two parentheses inside is the immediate reward R, plus I have to maximize what is expected from the new state that I'm going to land in, which is S prime, over all the possible actions, which are A prime. Okay, so this maximization is done over all possible actions. Now this gives me this new estimate, and then I'm going to do the minus alpha Q, which that was part of the 1 minus alpha. So we have the minus QSA at the end. Okay. Any questions so far? Okay. Now the update equation is almost, yes?
Question. Regarding alpha, how you decide alpha?
It's if it's very small, then you are going to update in a very large number of iterations. It's going to take a lot of time to do that.
Yeah.
If it's very large, then it's going to be fast, but it may not be accurate. So it's something you try. And we don't go into this, we show them some numerical examples where they can try the effect and see, but we don't go behind the math. How does it affect convergence and all that? Although this slide says between 0 and 1, I gave numerical examples where you can even assign values greater than 1, and it would still work in some scenarios.
Yeah,
so we don't go into these details.
Dr. Ashraf, let me just share with you this information. I asked this question because in statistics, we teach the exponential smoothing and the double exponential smoothing, which I think it will be the next topic or the next slide. Now, in the exponential smoothing, we use method, which is ARIMA method to evaluate alpha. Is anything related to this ARIMA method or ARIMA algorithm, or just you try it by guessing value and then you try to converge the optimal one?
Methods you are mentioning.
Yeah, I know, but I can tell from the similarity.
Yeah, because we are not going to that level.
You choose alpha. You choose alpha.
We choose alpha, and we ask the students to apply the algorithm.
I see. Okay.
Yeah.
Thank you very much.
They are not experimenting and finding the optimal alphas.
I see. I see. Thank you very much.
Okay. So the next slide as he said, we introduce another parameter which controls how much do we trust the new estimate from the new state S prime, which is gamma. Okay, so this is another also hyperparameter that needs to be determined before this algorithm is executed. And now the update equation is complete. Okay, so now we keep updating until the Q matrix is completely converged. Let's assume that the Q matrix is converged. So now when I am in a specific state, I know what action to take. It's the action that gives me the maximum estimated reward towards the goal. Okay. Now, if I keep doing this, this would be the greedy policy. Okay, this would be the greedy policy because every time I am in some state S, I will choose the action A that maximizes my estimated reward towards the goal. Okay, is that good or bad? Well, let's look at this example. Let's assume the AI was training using this world, and for some reason it got the path, which is the solid line, which makes the robot reach the goal, but through this long solid line, yellow solid line. Okay, and this got reinforced and re-emphasized in the Q matrix. So every time it's in a particular square, it knows what action it should take to go all the way until it reaches the goal. But it may not have tried the dotted line. Okay, and therefore the Q matrix that it has does not specify the Q line, or the values there are not really emphasized. They are not probably maximum so that they can be selected. Okay, and therefore, if you always play the greedy algorithm, which is always selecting what is maximum found in the Q matrix, you are actually depriving the AI from exploring what has not been explored before. And therefore, we get to this epsilon greedy decision-making policy, which actually is something called explore versus exploit. So if you are going to always use the maximum found in Q matrix, which has been developed using the build of the Q matrix, it means you're always going to exploit it. But you want to leave some room for exploring and innovation. Maybe a better path is found, and with trials, it could be built. Okay, and it becomes a viable path and maybe a better path than the other existing paths. And this epsilon greedy is with, again, another parameter with probability epsilon. We select some probability epsilon, and we say that with 1 minus epsilon, we choose the estimated best move based on the Q matrix. Okay, with some specific small probability epsilon, we actually don't choose the maximum. We choose a random move. And basically, this allows us to explore and find probably new ways to reach the goal. Okay, with this, we give all the material. This is all the material that we give the students in regarding to the reinforcement or Q learning. And we finish this by example of a very simple robot that tries to maneuver between rooms of a particular floor plan. So let's imagine we have, I don't know if I have, we have like this floor plan where we have rooms A, B, C, D, and E, and there is the outside F. Now, when the robot maneuvers between the rooms, there are doors. So from a particular room, you can reach some other rooms, but not others. And those are indicated by zeros. If you reach the room, it is 0. But if you cannot go into that room, for example, from A, you can go to only E. Okay, according to this floor plan, from room A, you can go to room E only. Okay, and that's why you have dashes all the way, except in E, there is a 0. Okay, and we want to reward the robot if it finds its way all the way to the outside. So every time the robot crosses the door to outside, like for example, from B to F, then the robot is rewarded by 100. when it crosses from B to F, it's rewarded by 100. And similarly from E مثلا to F, it's the same. Okay. And so now this immediate reward matrix is the R matrix that I was talking about. This is the one that's specified and as a feedback to the AI algorithm. Okay. Now with this in mind, we start with a matrix of Q, which is zeros. So the robot doesn't know where to go and how to make the decisions. Okay. So we want to consider this game. So this game has 6 states, A, B, C, D, all the way to F. And we can start at any state. It doesn't have to be. So and whenever we reach F, we end the game. Okay. And hopefully every time we play, we update the respective Q matrix input. For this specific game, we are going to use alpha equal to 1 and gamma equal to 0.8. Okay. So for these particular values, the update equations have a specific form that we will be using. So initially, the Q matrix is going to be 0. And we are assuming this reward matrix, which is based on the floor plan that I showed you. And the dashes, as I shown here, are the places where you cannot make the transition. For this specific problem, the states themselves are the actions. Why? Because in every state, I have only one action. If I go through the door, then I move to another state, and that is considered an action. Just, for example, I am in state B. My action D is going to room D because there is a door between me and between B and D. So my action D is actually going to room D. And my action F is going to the door that leads me to F, which is the outside. So in this case, it's a very simple problem. The states themselves can also represent the actions. Okay, now we start the problem as game 1. The game 1 says, let's randomly pick a state. Let's assume this state is B. So we start from room B. We have 2 options. We can either go to D or we can go to F. Okay. And now the AI will select randomly which one to go to. Okay. So there are 2 options to go from B, and it can either go to D or can go to F. If it selects F, then let us now this ends the game, right? So now let us consider that we are in state F, and from state F there are 3 possibilities, right? We can go to B, and we can go to E, or we can go to F itself. Now we want to update the input. They want to address, the Q matrix. The entry that we are going to update is the QBF because we were in state B, and we want to update the QPF. Now the formula is the immediate reward plus gamma times the maximization over all the possible actions in the F state. Okay. So the immediate reward is 100 because you can see that it's 100 here. It's 100 here. Sorry. And then gamma is 0.8. And then from the state F, if you look at all the Q entries in the row F, we have all zeros. So it's 0.8 times 0 plus 100 is equal to 100. And that updates the entry for BF. Okay, that updates the entry for BF. And now we get now QBF is equal to 100. Now, since we reached F in one shot, we started from B, we landed in F, it means the game is over. But we ended up with one update of QBF. We play another game. In this game, we choose another initial state, D, and we play the same game. But in this game, we can see that there are more than one step because we don't end up in a terminal state or a goal state immediately. For example, here, when D, we have options to go to B, we have options to go to C or E, okay? So we have to select one of these randomly. Let's assume we select B randomly. So it means we need to update QDB. We follow the formula. So what's the immediate reward between D and B? We get that from the R matrix, okay? And then we plus omega plus the gamma, which is maximizing over all the actions taken from state B, okay? And in there, from state B, if you go for the Q matrix, we have some entry which is equal to 100, which is QBF. QBF is 100, but the other QBD and the other QBD is 0. So we take 100, so it's 0 plus 0.8 times 100 is equal to 80. Now we got an update for QDB, okay? And we update the Q matrix as shown, okay, as shown. Now the game did not finish because now I am in state B, okay? I have to play until I reach F. Now in state B, again, I choose, I have options. I can choose D or F. I choose F, and if I choose F, I have to update QBF in the same manner, and it will end up the computation that QBF is equal to 100. So there is no change in the Q matrix this way. But I have reached a goal, the goal state, and therefore my game is ended. So I played game 1, I updated 1 entry. I played game 2, I did 2 computations. I did 1 update and 1 no change. And I keep doing this. If I play enough number of games, then this Q matrix, we can show that, and we showed this actually numerically in class, it will convert to the values that are shown here, okay? And now if I normalize these to maybe a 1 or 100, and now this Q matrix can serve as a guide to what should I pick when I'm in a given state. So for example, it shows if I am in state B, then the best thing to do is to go for F, which has an estimated reward of 100. Whereas if I go to D, it's an estimated reward of 64. So the best thing to go is for F. So this is what I meant, is that we have the procedure to build this Q matrix through this large number of playing games. And then when the robot has computed this, or the AI has computed this Q matrix, we can use that to make decisions. Now, I will just show you that there is a demo here for a NIM game. Okay. I will just let me just share it. And that will be the end of this presentation.
Doctor, we cannot hear this.
Sorry, doctor, there is no sound.
There is no sound?
In the video, no, sorry.
How do, I mean, it's not taking the sound.
Dr. Ashraf, you have to stop the sharing and start the sharing again. And when you share the second time, you have to enable the sound.
Okay, so I stopped the sharing.
Okay. And when you start the sharing, there is enable sound.
Start the sharing. Okay.
There is a small checkbox, enable sound from there.
How do you do the sound then?
No, before you click on the share button, there is a small checkbox somewhere. Can you please stop the sharing again?
I will stop the sharing.
Click on the share button.
Now I will select this one, and there is, okay, shared sound. Okay.
Exactly.
So sorry for that.
Represented each pile as an individual row. So you've got one object, agent how to play a game. You just let the agent play the game a whole bunch, and then the reward signal happens at the end of the game. When the game is over, if our AI won the game, it gets a reward of like 1, for example. And if it lost the game, it gets a reward of -1. And from that, it begins to learn what actions are good and what actions are bad. You don't have to tell the AI what's good and what's bad, but the AI figures it out based on that reward. Winning the game is some signal, losing the game is some signal, and based on all of that, it begins to figure out what decisions it should actually make. So one very simple game, which you may have played before, is a game called NIM. And in the game of NIM, you've got a whole bunch of objects in a whole bunch of different piles, where here I've represented each pile as an individual row. So you've got 1 object in the first pile, 3 in the second pile, 5 in the third pile, 7 in the fourth pile. And the game of NIM is a 2-player game where players take turns removing objects from piles. And the rule is that on any given turn, you are allowed to remove as many objects as you want from any one of these piles, any one of these rows. You have to remove at least 1 object, but you can remove as many as you want from exactly one of the piles. And whoever takes the last object loses. So player 1 might remove 4 from this pile here. Player 2 might remove 4 from this pile here. So now we've got 4 piles left, 1, 3, 1, and 3. Player 1 might remove, the entirety of the second pile. Player 2, if they're being strategic, might remove 2 from the third pile. Now we've got 3 piles left, each with 1 object left. Player 1 might remove 1 from one pile. Player 2 removes 1 from the other pile. And now player 1 is left with choosing this 1 object from the last pile, at which point player 1 loses the game. So fairly simple game, piles of objects. Any turn you choose how many objects to remove from a pile. Whoever removes the last object loses. And this is the type of game you could encode into an AI fairly easily, because the states are really just 4 numbers. Every state is just how many objects in each of the 4 piles. And the actions are things like, how many am I going to remove from each one of these individual piles? And the reward happens at the end. That if you were the player that had to remove the last object, then you get some sort of punishment. But if you were not, and the other player had to remove the last object, well, then you get some sort of reward. So we could actually try and show a demonstration of this, that I've implemented an AI to play the game of NIM. All right, so here, what we're going to do is create an AI as a result of training the AI on some number of games that the AI is going to play against itself, where the idea is the AI will play games against itself, learn from each of those experiences, and learn what to do in the future. And then I, the human, will play against the AI. So initially, we'll say train 0 times, meaning we're not going to let the AI play any practice games against itself in order to learn from its experiences. We're just going to see how well it plays. And it looks like there are 4 piles. I can choose how many I remove from any one of the piles. So maybe from pile 3, I will remove 5 objects, for example. So now AI chose to take 1 item from pile 0. So I'm left with these piles now, for example. And so here I could choose maybe to say, I would like to remove from pile 2, I'll remove all 5 of them, for example. And so AI chose to take 2 away from pile 1. Now I'm left with 1 pile that has 1 object, 1 pile that has 2 objects. So from pile 3, I will remove 2 objects. And now I've left the AI with no choice but to take that last one. And so the game is over, and I was able to win. But I did so because the AI was really just playing randomly. It didn't have any prior experience that it was using in order to make these sorts of judgments. Now let me let the AI train itself on 10,000 games. I'm going to let the AI play 10,000 games of NIM against itself. Every time it wins or loses, it's going to learn from that experience and learn in the future what to do and what not to do. So here then, I'll go ahead and run this again. And now you see the AI running through a whole bunch of training games, 10,000 training games against itself. And now it's going to let me make these sorts of decisions. So now I'm going to play against the AI. Maybe I'll remove 1 from pile 3. And the AI took everything from pile 3, so I'm left with 3 piles. I'll go ahead and from pile 2 maybe remove 3 items. And the AI removes 1 item from pile 0. I'm left with 2 piles, each of which has 2 items in it. I'll remove 1 from pile 1, I guess. And the AI took 2 from pile 2, leaving me with no choice but to take 1 away from pile 1. So it seems like after playing 10,000 games of NIM against itself, the AI has learned something about what states and what actions tend to be good, and has begun to learn some sort of pattern for how to predict what actions are going to be good and what actions are going to be bad in any given state.
So this is all the material that we have. By the way, this notebook is also available. There is a link for it on NIM game. So this concludes the material on machine learning using supervised and unsupervised learning and semi-supervised. Any questions before we finish?
Reinforcement learning can be a very
Let me go back to the slides. Any question?
I think since there are no questions, so maybe we'll
Thank you,
break
Doctor.
here and we'll come back after the
Okay. Thank you all.
lunch.
Thank you very much.
Thank you so
Dr.
much.
Ashraf. I shared the slides and
The slides are shared on the chat box.
Yes.
And they are also available in the Blackboard.
The Blackboard. So
Yes.
you may want for the second part to upload the notebooks so that if you want to go with me when I go over them, and also we have the slides if you like to see the PowerPoint version. So see you inshallah at 1 o'clock.
Okay. Assalamu alaikum.
So.